In my last video, we saw four curves: the circle, the ellipse, the parabola, and the hyperbola. Chopping up of a cone is not the only way to represent these four curves. It can be done in a different way too. And for this particular way, we'll need a point and a line. This point is the focus and this line is called the directrix. Using these two, we can represent any one of these four conic sections. Let's say I have this ellipse over here. If I draw a line from the focus to any point on the ellipse, and from this point I subtend a 90-degree angle onto the directrix. Let's just call this point P for a point in the curve, and this point is F for the ellipse, and let's just call this point M. You would find that the ratio PF by PM is always a constant. And we can extend this to all other cases, all other curves as well. Let me do that in a different color. Now I have this parabola, and with the same focus now, and I'll draw, let's just call this P1, and this point will be P2, and that's my 90-degree angle. This is M1 and this is M2. I'll find that the ratio P2F by P2M2 is another constant. Note that these two constants won't be same, as they are representing two completely different curves. This one happens to be an ellipse and this one is a parabola. And let me take a different color for the hyperbola. Another curve on the opposite side, and this is a hyperbola. Now I'll draw another line to the hyperbola and call it P3, and right angle onto the directrix, and this is M3, and then I'll find that P3F by P3M3 is another constant. I can intuitively deduce from this picture that this particular constant, okay, I'll just name these constants. I'll call this the hyperbola constant. This is the hyperbola constant. This one is the parabola constant. And this one is the ellipse constant. In this ellipse constant, I find that the PF over here is kind of shorter when you compare it to PM1. So what I can say about this is PF by PM is less than 1. As for the parabola, though it isn't very clear over here, the parabola constant actually equals 1 for every single parabola every single time. As for the hyperbola constant, it's easy to see that this hyperbola constant is greater than 1 every time. These three constants, the ellipse constant, the parabola constant, the hyperbola constant, are all come under one name: the eccentricity. The eccentricity of a curve. The eccentricity of a curve is a measure of how uncircular the curve is. I haven't drawn the circle over here. Actually, if I do draw a circle over here, a circle is a figure with eccentricity 0. That is, its ratio is, this particular ratio would be 0. A circle is also a special case of the ellipse, so it makes sense that this ratio is 0, which is less than 1. The eccentricity E would be given by this particular ratio, PF by PM. I'm generalizing this case to suit for all of our curves. P is the point of the curve, F is the focus, and M is the point where it subtends the 90-degree angle onto the directrix. So the eccentricity is given by PF by PM. Now I can do this. For the ellipse, the eccentricity is less than 1. For the parabola, the eccentricity equals 1. And for the hyperbola, the eccentricity is greater than 1. For the circle, the eccentricity is 0. Another special case that I would like to take is the case of the directrix. If I increase my eccentricity so much that the curve moves from being a hyperbola to a straight line as the directrix is, the directrix doesn't actually have a PM. So the eccentricity of the directrix, would be infinity, since its PM tends to 0. Let me define my next conic sections term with this case of the ellipse. An ellipse has two foci, which is the plural for focus. I'll call this focus F1 and this focus F2. We have this special line called the latus rectum, and the latus rectum is the line that runs parallel to the directrix and passes through the focus. So this line, which is parallel to this focus and which is parallel to the directrix and passes through the focus, and this line too, parallel to that directrix and passes through this focus. These two lines would be the latus recta of this ellipse. In the case of this parabola, I have the focus F, and approximately this line would be the latus rectum of this parabola.